Hello everyone, I'm thrilled to have you join the online course Easy Geosteering. We make complex geosteering topics simple by breaking them down into easy-to-grasp concepts. We are currently in the third part of the course, Geosteering Tools, and in the previous video we covered cross-section coloring. And today we start exploring the first geosteering tool, model method. Let's get started. Okay, the heart of the model method is the modeled curve. It is the offset well curve projected onto the horizontal well along geosteering horizons. Gamma ray resistivity and density, any offset well curve can be transformed into modeled. Here is our example, and the modeled curve is the red one on the horizontal track. To generate the modeled curve, we take the offset gamma ray from the vertical track and project it onto the horizontal well along horizons. Let's take one point, for example, hard layer with gamma ray level of 5.9 microrangens. We take this point and move it parallel to the geosteering segments until it intersects with the trajectory. Once we get the intersection, we mark the gamma ray value of 5.9 on the horizontal track, and one model point is now ready. To obtain the entire curve, we repeat this process for every single point from offset well. Of course, this is done automatically by the software. Okay, we got the entire modeled curve. What's next? Since the modeled curve depends on the geosteering model and can change its shape, we need to adjust the geosteering model until we have the best correlation between the modeled and real-time curves. In our example, we have strong correlation, which means our model is close to reality, and the local geosteering task is solved. We know where we are and where to drill next. Okay, let's discuss what the modeled curve depends on. As we saw, the position of the model point on the horizontal track is determined by the intersection of the trajectory and the respective horizon. This means the modeled curve depends on the segments, their number and dip. If we change one dip in a single segment, the intersection point will shift, which in turn affects the shape of the modeled curve in this segment. The second point is the horizontal well itself. If we keep the segments but place a different trajectory on the cross-section, we will get different intersection points and consequently a different modeled curve. It might happen, for example, when we switch from MWD trajectory to the geophysical one after drilling landing section. And finally, the offset well data plays a role. If the hard layer had, for example, a gamma ray of 5 microrangens, the model point would also show a value of 5, changing the shape of the curve in this point. Okay, and a few words about the name of the method. You may also encounter alternatives such as dynamic curve, synthetic curve, or comparison method, since it essentially involves comparing two logs with each other. Okay, let's explore the shape of the modeled curve in more detail with simplified examples. Here we have offset gamma ray with 60 API inside target layer, 90 API in the bottom and 120 in the top. By the way, such a geological condition is the best for geosteering because we can easily identify where we are, since 3 different formations have different gamma ray levels. For the first case, let's imagine the target layer is subhorizontal and we perfectly drill the well inside it. How will the modeled gamma ray look? In the landing section before T1 it will be 120, after T1 it will be 60 since the entire horizontal part remains in the reservoir. But what if we change our model so that the formation starts dipping up? To do this, we need to add a second segment and increase its dip. As a result, at some point the horizontal well will enter the bottom of the reservoir, and at this point the modeled curve will increase from 60 to 90 API. Okay, if we want to model the formation dipping down, we need to decrease dip of the second segment. In this case, the horizontal well will enter the top and the modeled gamma ray will increase to 120. Okay, we have covered how segments affect the shape of the modeled curve. Now let's see how the trajectory can influence it. To do this, just for example, let's take a completely different well and place it on the same segments. It doesn't make much sense in practice, we're simply illustrating the theory behind the model method. Imagine that we have a winding trajectory that enters both the bottom and the top at different points. The shape of the modeled curve will be a bit more complicated than in previous cases, but still in the bottom part it will be 90, in the top 120, and in the target layer 60 API. And finally, let's consider how offset data influence the modeled curve. Imagine that a thin hard layer appears inside the target close to the bottom. With the current trajectory, our well will cross it twice, and at these points the level of the modeled curve will also decrease to the level of the hard layer in the offset well. Okay, next. As mentioned before, when we have a good correlation between curves, it means our model is close to reality. However, in real work, we often observe some intervals with low correlation. What does it mean? The root cause of these mismatches is the different types of lateral changes. It might be thickness changes of some layers or presence of local geological bodies along the horizontal well, which do not exist in the offset well. In the second case, no matter how we try, we cannot establish a correlation between the curves, and we also cannot predict the appearance of these bodies, since it occurs randomly. The level of lateral changes completely depends on the specific geology of the oil field, but to some extent it always plays a role in our work. Okay, let's summarize the topic and repeat the workflow of the method. First, we need to transform the offset well curve into the modeled, then we compare it with real time, and then adjust the segments to achieve the best correlation. When this is done, it means our model has a high probability of accuracy, and we know where we are. Then, as we receive new real-time data, the second and third steps are repeated in a continuous cycle, and we do it every pipe or every stand. As a result of this method, we determine the borehole position on the cross-section and the formation dip in the drilling azimuth. Okay, next. This method can work properly under two assumptions, and the first one is the absence of lateral changes. If there are no strong lateral changes in the drilling area, we can achieve a good correlation between the curves by adjusting the segments. However, if there are strong lateral changes and the current and offset wells have significantly different log shapes, it may be impossible to achieve a match between the curves. Second point, we most often assume that all layers have parallel boundaries. Of course, in real geology, this is not always the case, and for now, most software can also model thickness change in the structure. Okay, and now let's discuss pros and cons of the model method. First of all, it is the most widely available geosteering tool since it's a low-cost software solution. You can use it even if you have at least one offset well with at least one gamma curve recorded. But it also has a few disadvantages. The first one we have already mentioned, it works poorly in cases of high lateral changes. The second point, if we have a similar gamma ray at the top and bottom of the target, we cannot distinguish between them using only one modeled curve. This means we don't know for sure where we are and where to drill next. That's why different geosteering methods exist. For example, borehole images can help in this situation. Point number 3, a reservoir with a great number of thin sublayers inside. In this case, it's very easy to confuse one sublayer with another, leading to incorrect geosteering model and recommendation. And the last one, low data density of modeled curve in horizontal section, and it's just a result of geometrical projection. When we drill parallel to the bed boundary, we take very few points from the offset well and use them for the long horizontal section. As a result, the modeled curve looks like a set of straight lines, making it hard to find the good correlation. However, despite all these weaknesses, this method is used everywhere, and almost every single horizontal well around the world is drilled with it. Alright, we have covered the theory behind the model method. Hope you like this video. Now you have a general understanding, and the next step is to practice. We have prepared a special exercise for you and real-world simulators. And if you would like to go deeper, just reach out to have a private session. So stay tuned and give this video a thumbs up. In the next lesson, we will explore the first real example for the model method. See you then. Bye-bye.